We are in Chapter 6, the normal distribution. This is section 6-4. This is video number 2. All right, so where we left off is example 6-16. Now, it's been the concept here is that 25% of the drivers have fallen asleep. You pick 200 drivers at random, find the probability that 62 will say that they have fallen asleep while driving. Now, when you first see this problem, it's very easy to be misled. If you were to see this on an exam type of a situation, you look at because it says that you take 200 drivers, you're going to be thinking, well, this sounds like the central limit theorem. It sounds like, Mr. Cantrell said that if you have a sample, it's going to be an X bar, etc., etc. Well, all I can tell you, folks, is that you have to just understand the distinction here. What we're talking about here is we're talking about an experiment, basically, a binomial experiment. Sometimes other authors will call it a binomial trial. Okay, what's the trial? Well, first of all, what's the variable? What's the random variable? The random variable is falling asleep. Okay, what's the probability that somebody will fall asleep? 25%. So a probability of success is 25%. So it's just like flipping a coin. Instead of asking about the probability of getting a head or getting a tail, we're asking the probability of falling asleep or staying awake. But this is exactly the same concept. It's a binomial situation. Okay, so you pick 200 drivers. So just like before in the previous chapter when we talked about the binomial distribution, you have a sample of 200. Okay, so it's basically 200 trials, so to speak. So 200 drivers are selected. Find the probability that 62 will say that they have fallen asleep while driving. Okay, so you understand the question, you understand the problem. Okay, so P is 0.25, Q is 0.75, N is 200. Okay, so check to see if a normal distribution can be used. Obviously it can, because 200 times 0.25 is 50, 200 times 0.75 is 150, that's more than 5, therefore we're good to go. All right, so now the mean and the standard deviation is perfectly easy to find. NP, mu is NP, sigma is square root of NPQ. Verify the math there. So the mean, the expected value, is 50. One standard deviation is 6.12. Okay, so the next step, write the problem in probability notation. We want to know what the probability that X is equal to 62. So remember, X is the number of successes. A success here is falling asleep. Just like before, we would say a success is getting a tail, or a success is getting a head. Okay, so I'm sorry. Okay, so we want to know what the probability of X is equal to 62. X being people that fall asleep. That's a success. It's always better to think about these in terms of successes. A success being flipping a coin and getting a tail. A success being you live. Success being you die. Whatever the situation is. In this situation, success is falling asleep. Okay, so now we're going to rewrite the problem. Okay, and for 62, X is equal to 62, you can see right there, that's 62 is right there. The continuity correction is to go from 61.5 to 62.5. So it's this interval right here. So the area under the curve makes sense, okay? So that's going to be the probability. The approximate probability is going to be the area under the curve. Now you'll notice on the electronic edition of the book and in the paper edition, they have a little typo here. They have this area coming up here, right? Well, that doesn't make any sense. Unless it's just artistic license and he's saying, well, the 62 is this guy right in the middle here. I don't know what he means by that. But normally what most authors would do is they would make this very clearly an area under the curve. It's the area of the rectangle is what most people say. It's not exactly a rectangle, obviously, but it's the area under the curve. So by having it above the curve, it makes it a little bit awkward. Okay, so in any event, what we now want is we want this area underneath here. We want to find the corresponding z values. Okay, we've done this before. So the z1, we're going to say is the 61.5. The z2 is the 62.5. There it is. So you remember how to do this. It's x take away mu over the standard deviation. Okay, so I guess I'll let you confirm that these numbers are correct. So the area to the left of 1.88 is 0.9699. The area to the left of 2.04 that corresponds to this is 0.973. So the area between those two guys, you just do the subtraction. Okay, so it's about 94%. Okay, two big mistakes here. I apologize. I'm just not good enough at editing these tapes to go back and change it. I said 94%. Obviously, that's not correct. It's 0.94%. 0.94%. In other words, it's less than 1%. So roughly speaking, it's about a 1% chance that 62 people will fall asleep. Okay, where are we at here? 62. The probability that 62 out of the 200 will fall asleep is a little bit less than 1%. So I made a mistake when I said 94%. I don't know where that came from. And then there's this kind of a typo here, and then there's a typo right here too. Find the corresponding z values. It says since 72 represents any value between 71.5 and 72.5, find both z values. Where did 72 come from? That doesn't make any sense. It's just a typo. This should be 62. This should be 61.5, and this should be 62.5. So I hope you can see that. Okay, so I guess just to sum it up, you could calculate this using the binomial theorem, or the binomial, not the binomial theorem, the binomial distribution. You could do the calculation. It would be horrible. It would be, you'd have to take, hold on one second. Okay, so here's the formula from the back of chapter 5. The formula for, I'm sorry, where did the heck they go? Right there, the binomial probability formula. The probability of 62 successes would be in this situation, n is 200, so it'd be 200 factorial, and then it'd be n take away 62, that thing factorial, and then 62 factorial. I mean, it'd just be a mess, right? And then here it would be p is the probability. So in this particular problem, we decided that p was the 25%. I think that was it. Let me look here. Yeah, 25% of the drivers fell asleep, right? So 25% chance of success. So it'd be 0.25 raised to the power of 62. I mean, forget about it. Who'd want to do that, right? It'd be way, way, way too hard. Okay, so clearly it is way too much trouble to use the binomial distribution. It's much, much easier to use the normal approximation. Okay. All right. I guess that's all I got to say about this problem. Let's take a look here. Ragweed allergies. Okay. So here's another perfect example. This is ragweed allergies. Okay. 10% are allergic to ragweed. You could change this around a little bit to be appropriate or relevant to our current situation with a COVID illnesses. Let's say instead of being 10% are allergic, you could say 10% are at risk. So you could easily change this into a problem that might be a little more topical for us. In any event, this problem is 10% are allergic, 200 people are selected, find the probability that 10 or more will be allergic. Okay, so how would you solve this? Before you learned about this, the normal distribution, you'd have to say, well, gosh, 10 or more out of the 200. Well, one way you could look at it is you could say, well, 10 or more, that's the complement of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, not being allergic, right? So it's the complement. You could solve it that way, make it a little more doable, a little more feasible to do it, but it'd be a horrible calculation to calculate the probability of getting of 0, the probability of 1. It would just make you nuts, okay? So we're going to see how easy this is using the approximation. Okay, the first thing, we make sure that we can use it. P is 10%. I'm sorry, where did that go? Oh yeah, 10% of the Americans are allergic. Q is 90%. N is 200. You multiply these guys out, they meet the requirements. We can use the normal approximation. We can find mu, we can find sigma very easily. We just crank that out. We write the problem in probability notation just to kind of keep us straight, so to speak, okay? We're going to use the continuity correction factor in order to do this, okay? And then we draw another cartoon. Here's our cartoon. We want to know 10 or more. So the mean is 20. Okay, here's the mean. It's 20. 10 or more is 10 this way, all right? However, we have to use this continuity correction. So what we do is we go to the left a little bit. How far do we go? We go 1/2 of the digits that we're using. Since we're using whole digits, we're using 10. We go to the left by 1/2. So it's 9.5. Now we don't need anybody over here because we're not finding the area under this curve, like we did before. We're finding the area under the curve all the way from the left, from this point right here, all the way this way, because we want to know the probability of more than 10. If we just started it at 10, it would not quite be correct. We need this correction factor here, okay? All right, so now it's very, very simple, right? We find the z, the z that corresponds. This is a normal distribution, mu of 20, okay? Has a standard deviation that was given to us. Standard deviation. I'm sorry, the standard deviation is right here. Sigma is square root NPQ. Boom, there it is, 4.24. Okay, so we know everything we need to know. We've got our mu and we've got our standard deviation. Do me a big favor and always write down the equation. Don't do it like the author does it. It's just the source of so many errors. I've been doing this for more than a week or two. I know what I'm talking about. Write down that equation. So it's z equals x take away mu over sigma. So there it is, negative 2.48. The area to the left of negative 2.48 using the table is this. The area to the right is going to be 1.00. Take away that, so it's 99. It's 0.9934 or 99.34%. So our conclusion is, you pick 200 people at random. The probability of 10 or more of them being allergic is 99.34. So think about it in terms of viruses. You can see exactly why this would be important for Dr. Fauci is the guy that's the head of the CDC section that's dealing with this. You can see why he needs to know this kind of stuff, okay? I guarantee you that he knows it. Okay. Okay, the next problem is exactly the same. There's batting average here, but now we're talking about less than a certain amount. So I'm going to leave that one to you, okay? This next example here, example 6-19, I think is very important. So I'm going to stop this video now and resume the next video talking about this exact problem.